Okay, welcome to lecture 9. The main topic of today's discussion will be unique decoding the Reed-Solomon code. So starting actually from today's lecture onwards, so far we've been looking at coding theory more from a combinatorial point of view or a linear algebraic point of view. We didn't bring in algorithmic issues into the picture. So starting today, we will begin looking at several codes and looking at what are the algorithmic issues that come about. So even before we plunge into Reed-Solomon code, let's ask what are some algorithmic issues that can arise when we're looking at. So when you're looking at some code C, which would say in some alphabet signal to be C is N K Q. So we'll just list a bunch of questions that can come and ask, do we have algorithmic ones? The simplest of the questions is the encoding algorithm. Is the encoding process efficient? So what do I mean by algorithmic issues? What I mean is all of these, we have combinatorially defined these objects. So there is some underlying process. There's always a finite process that does this. Okay? Question is there an efficient? By efficient, I talk in terms of typically polynomial time, but if you want to be even more specific, we'll actually state it explicitly as. So one is the encoding question. The other is, of course, one is, so that's just, you give me a message, I want to find the code word. The other is detecting errors. Next question is, if you want to detecting errors. Has there been any corruption in my? Another question you can think of is now, suppose you want to correct the errors. The easier thing would be actually if the errors were actually erasure. What you know is something has got smudged out, but you know it has got smudged out. Not like it's not got a flip. So correcting erasures. And more generally, correcting errors. So for any code, so far we only talk about rate, dimension, and distance. Soon we will begin asking these 4 questions also for most codes. We have efficient algorithms accompanying for the code with respect to these 4 processes. Later on, we will see there will be even more finer things. We can talk about local encoding, local decoding. We'll look at that later on. But let's start with most of today's lecture is going to be actually in item number 4 with respect to the Reed-Solomon code. But to begin with, let's ask these questions for any general code. So, what do you think? What do you think about encoding? So we already saw that certain code, most codes which we have talked about so far, for a large part, are linear codes. And linear codes come accompanied, we said that they have come accompanied with them a generator matrix. It's not always true that there is a generator matrix always, but if you also have the hands on your generator matrix, the encoding process is actually very easy. So the encoding is easy. So encoding is an easy process. So let's write down 1. In fact, 1, 2, and okay, that's 1. What about detecting errors? So the parity check matrix that was designed for this process, you can just apply the parity check matrix on the received word. And if you get the all zeros thing, you know that it satisfies the memory. So once again, here, the fact that it's a linear code is quite useful. So both 1 and 2, we sort of defined it for a linear code. If we had G and H with us, 1 and 2 are automatically efficient. What about 3? So basically, you have to ask how many erasures can you. This one, you look at the generator matrix times this one. There are some. Is it the generator matrix times? Yeah, the generator matrix times this one. You're asking if the system can be solved. If the system can be solved, it can be solved if the number of erasures is strictly smaller than the distance. So once again, in all 1, 2, and 3 are easy. easy if code is linear and we have access to the generator matrix, G and H. Okay. So, and most codes we have talked, all the linear code we are talking about, we made actually huge effort to find out what is G, what is H, and that's precisely to make 1 and 2 easy, 3 gets not easy. So 1, 2, and 3 are sort of, we will not dwell so much into it. These are actually in general if code is linear. So for instance, the GB bound, the Varshamo bound is a linear, you know that a random linear code, but it's not as if I have my hands on that. Huh? You don't have guarantee that the distance is good. It's you want a certificate, so I don't have a, so you can pick it up, but why do you know that it is? So if I actually want, so because that's, you know, a random one is good, but if you want a code, you have to give me a process that for every n will give me a generator matrix which is guaranteed to have a good distance, and I don't know how to do it. So you know this family exists. I don't know of an efficient way of laying my hands on this family. If I did that, I would have got a explicit curve that sits on the GB bound already. We don't yet have it. In fact, we don't. At least so far in the course, we haven't even got a code which is sitting in the non-zero part of the rectangle. Every explicit code is either on the x-axis or the y-axis. So far, more or less. Yep. Code is linear. This is. Now let's go. So the focus will be on code. So most of our issues will be actually doing code correcting things. Once again, so let's actually, in the case of one, so no, I'm not even defining how to do 1, 2. So when is one efficient for a nonlinear code? With the encoding process, when there is an algorithm that maps sigma to the k to sigma to the m, and you have an algorithm. That's exactly what the question is. If the one in for linear codes, G gives you such an algorithm. Of course, even here you could ask more questions. If you are given G, you only have a quadratic time algorithm. Because G is going to give you a matrix vector multiplication way of solving. You could go ahead and ask, even though it's more ambitious, you have a linear time algorithm that will match take the message to the code. That is not answered, and we'll see they've been answered to this question. We can construct linear code for which the encoding process is actually linear time and not quadratic. So, but in general, for right now, I'm going to not be that specific when I talk about efficiency. Efficiency will be polynomial when I'm doing most of the course. In the problem set, we'll ask you specifically how to make the algorithm more efficient, NCO and square. So encoding, so in general, encoding is efficient if you have this algorithm which can map. So then, so I should actually encode it. So first, we say encoding in general, encoding is efficient if this process sigma to the k, sigma to the n is efficient. And sometimes, usually we refer to code as a subset of this. Sometimes even this mapping is called the code. So sometimes then we'll abuse terminology. Sometimes we call this mapping to be the code, and sometimes just the image of this to be the code. And in general, we will only talk about for item 4. Item 4, I'm going to say given a code and a received word, I want to be able to correct the errors. Now the question is, what does it even mean to say given a code? For an arbitrary code. For a linear code, you can say, I give you the generator matrix of the code. For an arbitrary code, what does it mean to say given a code? We will say, I give you this algorithm. Give me this algorithm and the received word. Can you? So this is what. So I'll say a code is explicit if this. So this is going to be my definition of explicitness of a code.
In IT code, including even as or as
So it's not. So the problem is ill-defined. You can do it as a Oracle. That makes the problem a bit too. Actually, I give you the Turing machine, the algorithm. In most cases, it will be a specific code. So you have the generator, your hands on the generator. So the most general case of correcting errors is you are given an algorithm, your input, you're given this code, you're given the code for this explicit, you're given the algorithm for this, and then you're given a received word and you want to correct them. That's the general question. The question for code, the problem here with given a code, question is how via generated matrix or encoding that. And a received word R is in sigma to the n. Find n such that find C, this is the code, find C and C such that delta R and C is that's the general question in 4. That's the most general way I can phrase the problem in 4. Okay. By the way, there need not be a unique answer for this, in which case. Okay, what did I say? Okay. Stated in this generality, the problem actually becomes very hard. You can show it's actually NP hard. But it's one that the problem that is even for a specific code, even for the Reed-Solomon code, if I state the problem in this general framework, it's actually a very hard problem. And I'll try to see if I can put this in a problem. But even for Reed-Solomon code, I can give, you can give me. You can fix, so here there are two, the input has two quantities, the code and read. I said, even if you fix the code to be Reed-Solomon, I can give you a family of received words for increasing lengths, such that if you're able to find the closest code word in all of them, you'll actually be solving that. In this generality. But so we'll try to make the problem a little more specific so that it's actually doable. So there are the two cases of Shannon, the Shannon case and the Hamming's case. Shannon case will be, don't work for all received words. Take received words which are obtained by adding noise in a probabilistic sense to a valid code. Only as long as you can work only for those sort of errors, that's fine for Shannon. Shannon doesn't want, Shannon's work doesn't say you have to recover from every possible corruption. It only says most corruptions which are obtained due to the channel. So that's one way of trying to make. So what I want to say right now is this problem. So as stated above. As stated above, the problem is NP hard. Even for specific codes. Such as Reed-Solomon. But we still do want to solve this problem. We don't want to throw our hands up and say, oh, this is NP hard, I'm not going to solve it. So then you could ask, sort of a Shannon-like question. Can we solve it for most R that arise for a Shannon? So you might not be able to solve it in the first case, but yet, as long as you have an algorithm that solves it most of the time, this will answer Shannon's question. You could also ask Hamming's question, in which case you're not going to ask, in which case you don't solve the general problem. You say, I give you a guarantee that the received word is within T of a code word. In that case, you solve the problem. And this might not be doable for every T, but there are certain T's for which it is doable. So you give a promise that the promise is characterized by T. There exists a C in C, such that delta RC is less than or equal to. You give this promise, and given that promise, you can do it. And Hamming, in fact, did it for when T equals 1, he gave an explicit code. That way. Question is, so what we will do is we'll take Hamming's approach and we'll ask how large can T be made so we can solve it. Okay. So our approach will then we take Hamming way out. In particular, find largest T for which we can solve it. T should be d by 2. So if you want, so the question is what's the largest T? We will actually look in the course of the course, we look at T which are larger than T by 2. So combinatorially, what we know is if T is is strictly smaller than V by 2, then we know that they exist at most 1. So we can ask in that case, so what we know is combinatorially if T is strictly smaller than D by 2, there exists at most 1 C in C, such that delta RC is less than or equal to. And this is what is called the unique decoding. So if you want to get within the unique, you can ask up to this point, can I do it efficiently? So several codes having all sorts. The issue is not, we have seen lots of codes so far, but this issue is for Hamming, we know it to do it exactly up to D over 2. For BCH also, I didn't tell you, I gave you the code, I gave you read column, I give you read more, I never gave you the algorithms for them. It's unclear how to do the even unique decoding all the way up to half the this problem is called the unique decoding. Okay. Question. And people have been studying this question. Codes were introduced, of course, by Hamming and Shannon in the 40s, 50s. But people have been looking at algorithmic issues almost since the very beginning. And surprisingly enough, Reed-Solomon code was one of the earliest codes. What we will focus our attention is answering this question for the case of Reed-Solomon when T goes to half the minimum distance of the Reed-Solomon. So that's what will be the focus for today's lecture. For Reed-Solomon code, there was a lot of work that went into rate solvent. The earliest of the work is with Peterson. In 1960, gave an n-cubed algorithm to solve the rate solvent code. Notice this is even before P is first defined. So Peterson actually gave, or is possibly one of the earliest, and Peterson says why his algorithm is nice is because it's an efficient algorithm. Notion of efficiency was not yet well defined at that point of time. The definition of P came much later, in the late 60s and early 70s. Peterson. And strictly speaking, Peterson didn't solve it for Solomon. Peterson solved it. What? So yeah, that's exactly. So Peterson did not solve it for Reed Solomon. What he solved it for was PCH codes. So the PCH codes we used last time, they were discovered even before Reed Solomon. So what Peterson solved was for the PCH codes. And Gorenstein and shortly after when once it was realized that BCH is actually a subcode of Peterson of Reed Solomon, Gorenstein and Taylor observed that Peterson's algorithm actually works even for the Reed Solomon. So quickly speaking, it's called the Peterson-Gorenstein-Taylor algorithm. And then later on, this was NQ. Then Berlekamp, what are the years of this? Berlekamp and Massey independently gave a sort of quadratic time algorithm for this problem. And this is commonly called the Berlekamp-Massey algorithm. It's two different papers, but it's now referred to commonly as Berlekamp-Massey algorithm. This has since then been considerably improved, and now we have nearly linear time algorithms, implementations of the Berlekamp-Massey approach to reform. So I think now we have nearly linear. And by that I mean order n polynomial. Time algorithms. Then Berlekamp himself, Welch and Berlekamp. Actually, it was that this was before the linear time was discovered. Berlekamp and Welch relooked this problem and said if you can actually come up with an order NP, T was the number of errors. If the smaller the number of errors, they could run fast. The errors could be as large as linear in n, in which case it becomes quadratic. It's like the Berlekamp-Massey, but what they observed is actually you can get an NP algorithm. And more recently, this is 1980. Huh? You can just, so they will just run it for is not known. I think you could just do binary search. You could just do binary searching. It might, there will be some polylog factors, but you can be done. Then Gemmell-Sudan in 92. They didn't do a new algorithm, they just gave a reinterpretation of the Welch-Berlekamp algorithm, which is what we will do in class. So, so that's the history of sort of Reed Solomon decoding. So this has all been in the unique decoding. Actually, the story doesn't stop here. So what we will do today is Welch-Berlekamp. Actually, we will not see exactly Welch-Berlekamp. We will see an interpretation and even other interpretation which will include all of them. I'll actually give you a sort of a common approach in which solves all of them and then tell you how these things differ. Which would, if you do this step this way, you actually get Peterson's algorithm. If you do it this way, you get Welch-Berlekamp. And the story didn't stop here. So Madhu will continue. And he asked what happened if P is larger than. What if P is larger than 0? Here you cannot uniquely decode any longer with P greater than 0. And so the L92, 95 for it. Actually, here the first this decoding algorithm for recall code, which handled errors more than PO. And then in 98, Goswami and Sudan. Got it all the way up to P being the Johnson. And that's where the story stops for Reed-Solomon code. The history is this one. It's open if Reed-Solomon is decodable beyond the Johnson treatments. It could be.
I didn't see least decoding Reed-Solomon code up to different formula that it will
So there are this one, so there are catches to this in the sense that so these algorithms, the way they are stated, work for any. So what do you mean by Reed-Solomon code? What do you mean by Reed-Solomon? It depends on the set of evaluation points. So these algorithms, at least the way we are going to present them, will be general enough that they work for any set of evaluation points. Now later on we will see. After this, the work happened after Goswami-Sudan is there will work which show that there are some set of evaluation points for which you cannot just decode beyond the Johnson radius because the list becomes exponential. So actually, Jayakumar in joint work with Peterson and Swastik Kopati have such a work. They show that there are certain choices of evaluation points for which if you sufficiently cross the Johnson radius, not exactly the Johnson radius, sufficiently cross the Johnson radius, the list size becomes exponential. So that's combinatorial reason why you can't have that. Then there are other reasons that for certain other problems, for certain other sets, not necessarily the evaluation sets given by Bensosan, Jackson, and Radhakrishnan and Kopati. So there are other things which are for these evaluation points, if you can solve it, you might actually be able to solve the discrete law problem. But it still leaves open that there might be certain nice set of evaluation points for which you could solve the Reed-Solomon code all the way up to this, or even above the Johnson. Right now, we don't know any algorithm that works beyond the Johnson. Okay. Today, Gemmell-Sudan. I will. Actually, Gemmell-Sudan doesn't only for Welch-Berlekamp, but I will sort of make it even expanded furthermore so that it covers all the Unique-decoding algorithms. Okay, so that's the problem. That's the thing we're going to focus today. So let's take the problem explicitly. What's the question? So input, you're going to state it in a more general one. The input you are given a finite field. Okay. And by this I mean if it's a prime field, if Q is prime, you're just told the proof of primality. If it is non-prime, you're given the proof of primality and you're given irreducible polynomial. That's what I say when I say given a field means. So in particular, you can do I can do addition, multiplication, division, and all of this in the field. Then you're given K, you're given S, which is a set of evaluation points. Size of S. And S is the positive. Given that, you're given K, which is the degree parameter. given T bound on the errors. And finally, you are given the vector beta prime, which is beta 1, beta 2, beta n. That's the received code. Yes. So that's the input. You're given 3, you're given this. What are we supposed to find out? Output. Find all polynomials P in f less than k x such that the number of locations I n such that P of alpha I is not equal to beta I is less than. Okay. That's the problem we will solve. We will solve it today's lecture when P is less than the. We will show that we will try to solve it this one. We will show that it stops. In fact, the algorithm will magically just go all the way up to half the unique distance of the resolvent code. It's not 12:30 or 1? 1. So this is what we want to do. So let's see how to come up with the algorithm. Now this is so let's make several observations along the way, and eventually once we have enough observations, that will automatically lead us into the algorithm. So what's the error? So let's look at the error set. So I'm going to build this error set, which is exactly those I in n. Exactly the one which I have written above. P alpha I is not equal to beta I. Notice if I knew the error set, the decoding is easy. It's now just a problem of erasures, and I know how to solve a polynomial iteration. So we don't have access to this set error. So given the input beta, I don't have this. By the way, because 1 second, I should say, to even talk about this. If P is less than or equal to, if 2T is less than B, there is at most one such polynomial. Hence, I can talk about what I call the errors. Because otherwise, it doesn't make sense to say what is this error set, because the error set unequal and let P be the unique polynomial with one instance. We don't know. Okay. Now, what we will do is we sort of work with polynomial. We build this notion of error locator polynomial. Okay, it's not so good, but yes. Error located polynomial is exactly going to be that polynomial whose roots are, whose zeros are the error locations. The polynomial with zero are the errors. More precisely, E hat is exactly product of x minus alpha I in. Okay. That's all. Okay. And once again, notice we don't know. Once again, if we know E hat, we can solve the problem, because once we have E hat, we can just go and find out what are all its zeros. Just try out all the points in the evaluation. Set, find out which are its zeros, and then we know E hat, we can go ahead and do erasure. So we neither have F nor E hat in our hand. The goal of all the algorithms we will design today is somehow to lay our hands either on E hat or on a multiple of E hat. That is, notice the erasure you can still solve if you know which are the, you need to know a superset of the erasures. As long as you know this, you will still be able to recover. So the goal will be to try to find out not either E hat or some multiple of E hat. Okay. As long as they are not, it's not too large. Of course, there's a multiple which is just I can take x bar cube minus x. Certainly, that's a multiple of E hat because it's the multiple of every such thing. That's not good enough. I want a multiple which is not of degree larger than. So now, given this E hat, let's list out a bunch of properties that E hat satisfies. E hat or yeah, E hat satisfied. Not just E hat, we'll say any of these other proxy for E hat will also work for us. The first thing which we want to say is E hat is it's not the all zeros polynomial. It's always one or something. Then even if the error set is empty, then it's actually then that's an empty product, it's one. And furthermore, it's not too larger. The degree of E hat is less than or equal to. Furthermore, what we know E hat is exactly the error locations. We know beta I is equal to P alpha I when the error location when I is not one of the errors. So this equality P alpha is equal to beta I. We want it to be an equality because a non-corrupted word, that's an equality all the time. Now it's not an equality exactly when I belongs to the errors. So if I multiply this with P of alpha I, it becomes an equality because, and that's the whole point of the error set. The error set is basically going to, previously this was only for I and E, not in the error set. We have that P alpha I into E alpha I, E hat alpha I equals beta I into E hat alpha. This is, notice the key point to notice over here is this holds for all I equals, not just I not in the error. Because when I is not an erroneous thing, P alpha I equals beta I. Otherwise, E hat alpha is 0. So even if the inequality were true, it ensures that the equality comes back between two. Okay, so that's an important, that's a key observation that we had. So notice this is true. Okay, this is an observation that we have. So let's now, given that we have this, let's define this polynomial. Let's define this polynomial to be a useful polynomial, n of x. Let's define it to be the polynomial p of x into E hat That's the definition. What do we know about n of x? What are some other properties we know about n of x? What's the degree of that's what we call it n hat? What's the degree of n hat?
E plus K.
E plus k. E plus k minus 1. The degree of p is k minus 1. So this is utmost. P plus k minus 1. That has one such degree. And furthermore, what do we know? That's one property. For all I in n hat alpha I equals beta I times e hat I. I'm just rewriting it. So once again, we want to lay our hands on E hat that satisfies some properties. So what we will do is now ask the question, can I find, so we turn around the question, ask question. Can we find poly E of degree less than or equal to E such that there exists an n hat of degree less than or equal to t plus k minus 1 that satisfies an. Certainly, a E which we want to solve has to satisfy this property. So let's find out if we can ask this question.
So, what's either degree bound of the
What? Sorry, not E. My mind, E and E are the same thing.
Okay.
By the way, E hat is a solution to this question. E hat need not be the only solution. There might be other E's. There might be spurious E's that satisfy the solution. But there are two questions to ask. Two things that we have. Firstly, can we solve this problem? This is a related problem to this one. Can we solve this question? And if we solve the question, is it useful? Once I solve this, I'll get some E. Not necessarily E hat. Is that E any useful for? So what I'm going to say is all the algorithms which we have seen so far are actually all solving this question. Whether it be Peterson or Berlekamp or Massey or Berlekamp, Welch-Berlekamp, they're all solving this. They're all laying their hands on it. How they go about doing this is they have different ways of doing this. And then there's an analysis saying that from this E, you can complete this. Though this E might not be E hat, even from this E, I'll be able to go ahead and finish and solve the problem. Okay. Question? Okay, so for now, let's forget about. We have to ask. We have asked two questions. Can we find such an E? And one is whether we can find such an E, and is such an E useful?
So, there is a polynomial of like passes to beta I and
What?
so yes, so no, sir.
So they might not, for example, there's no unique key. For example, suppose we make there's a unique key. Certainly, any constant multiple of E is also a solution. But I haven't put the condition that E is monic. E hat was monic. I haven't put the condition E is monic. But furthermore, notice that any multiple of E hat, as long as the multiple doesn't cross degree T, is also a valid solution. Any multiple. And in fact, what we will be showing eventually is when you solve the system, the only thing you will get are multiples of E hat. Or you might get some solution, but that solution will be a multiple of E hat. But if it's a multiple of E hat, it's fine. You could have still gone ahead. You just go and find the zeros of that, throw it out, and you can solve the problem. So what we will be showing in the rest of the lecture is firstly show that this E can be solved. Such an E can be found easily. And whichever E you lay your hands on, actually this E is actually a multiple of E hat. If we show these two things, we are now. That's going to be our. Okay. Now,
You haven't anywhere used that previously.
I haven't used it. It will pop out in the analysis. Pop out. How do we find such an E? Why is such an E? We have to answer both these questions. So actually, Berlekamp, all the algorithms differ only in one. How they find such a E, the algorithms differ in how they lay their hands. And then eventually, then the analysis of why such an E is useful is more or less similar in all these. So how do you find such an E? So let's start off with the simplest thing. So what is such an E? I want to say this E is a linear system. So what is E? So therefore, E I can write it as, so basically, let's well, you want to find a polynomial of degree less than n, such that there exists n hat of this that satisfies the n p. So just come up with variables for the coefficients of E, coefficients of n, and ask if I can satisfy all that system of equations. So more, this is in fact this style of writing is exactly the Welch-Berlekamp. Step 1. Find n E pair of polynomials. Step 1. The degree of E is less than or equal to T. Degree of n is less than or equal to T plus k minus 1. 2 for all I in n of alpha I equals beta I times E of alpha. That's step 1. Step 2. Output n by E. That's center algorithm. And what we will see next is Wiles algorithm. The algorithm clear? We need to answer several things. Why is this algorithm efficient? And then why is it correct? Efficiency should be easy. So the first is just a system of equations. So let's ask. Efficient is the step 1. Step 1 is a linear system. In how many variables? What's the number of variables in the 2t plus 3 plus 2t. So because there are E has how many variables? T plus 1 variables. And how many variables does n have? T plus k, so 2t plus, exactly 2t plus k plus 1. That's the number of variables you have. What's the number of constraints? N, because you exactly have one constraint for each of them. It's a linear system. Is it a homogeneous linear system? In the sense, so it's a linear system. A linear system is it of the form Ax equals 0 or Ax equals b? Ax equals 0. There are no, once you write a linear system in the coefficients, there is no this one. It's a, so it will always have a solution. So find, so in particular, what I should tell you is find a non-zero. Any, that's important. Our system can go ahead and output one. And notice, for our setting of variables, it actually might be an over constraint system because t is less than n minus k by 2 plus 1. If you look at it, so the number of variables is less than the number of constraints. Therefore, it might be that this is an over constraint system. So it might not have, so it always has a solution. It always has a solution 0, and it might be the case that 0 is the only solution because it's an over constraint. So, but if by assumption E hat and N hat is a solution, so they will always be a non-zero. So if there is a close enough code word, they will be a non-zero solution. That's one way we will do it. So this is step 1 is efficient because step 1 is efficient in respect to all of this. Step 1 is 1. Step 2 is just division, so that's also.
What do you mean step 2 n by e is 1 and now?
So n by e, n is a polynomial, you're dividing it by another polynomial. This division, this quotient, need not be a, it could leave a reminder.
Yeah, so it's like a division in the real program, not in the finite.
No, it's a division, and it's so we told in polynomials, you give me two polynomials, n and e, you can write it. You can do n is equal to aq plus r. So eq plus r, you can do the division in the polynomial thing, and if r is non-zero, then output q is all I'm telling you. Follow what I'm saying? So yeah, it's regular polynomial division. It's polynomial division as we do it. Yeah. So it need not be that n need not be a multiple of e. In which case it's not a polynomial, so that step will hang. So I'm saying if it's a polynomial, hang output. And what I want to claim is if there is a code word close enough, no matter which solution you have, so what do we need to show? We need to show that. So we have to show the following two claims. One is the claim in one, if there exists a unique polynomial t such that there exists a unique polynomial, if there exists a polynomial, it will be unique with one such that what I'm giving delta number of thing n p alpha I is not equal to beta I is less than or equal to t, then there is a non-zero solution. So if there is a polynomial, then there is a non-zero solution. Claim 2. Let n1 e1 and n2 e2 be any two pairs of solution to step 1. Then n1 divided by 1 is identically equal to n2 divided by 1. And here is where I will use the assumption that p is less than n minus k plus 1. It's in this line for therefore, let's look at it. Let's look at both. I want to claim if both these claims were true, then they are done. Then they are good. Huh? any two non-zero. That is the solution. So step one, then we have this. So before we go into the proof of claim, both the proofs are actually fairly easy. Let's first understand why if claim one and claim two are true, then we are done. Because claim one says you can always find a non-zero solution. Therefore, step one will lay its hand on some solution, possibly not n hat e hat, some other NE. But claim two says as long as if there are any two solutions to it, the quotient will always be the same. In particular, n hat e hat gave you the right answer. Therefore, any other n will also have to give you the same answer. Okay. Proof of claim one is actually trivial, n hat e hat is a non-zero solution. So proof of claim two. So what we want to show is basically we need to show n1 e2 is identically equal to n2 e1 as polynomials. This is the product of two polynomials and the same as the product of these two polynomials. To show two polynomials are equal, we only have one. This one is a degree mantra. Show that these two polynomials are identical on more number of places than the degree of the two polynomials. Hence, they have to be the same polynomial. That's the only way we know how to do this. So we need to show this. We'll appeal to the degree mantra. What's the degree of n1 e2? Degree of n2 1. What's an upper bound on this? 2t plus k minus. So it's t plus k minus 1. So it's 2t plus k minus 1. Right? So that's the degree. Let's look at how many places are there. This one. So let's look at, so for all I in n, we have n1 alpha I, e2 alpha I. This is by construction. This is what is this? This is beta I, e1 alpha I. So n1 satisfied that n1 alpha I is equal to e2 I, e1 alpha I for all points. If I just did, this is true at every one. But now I'll plug this beta I with this guy, and you can go and now say this is e1 alpha I into alpha I. Therefore, for every point I in n, you have this equality. If n is larger than 2t plus k minus 1, then n1 e2 identical. Yeah, the proof is amazingly simple and clean. So once again, so what does the Berlekamp-Welch algorithm 2. It's an extremely simple algorithm. It looks at this. We want to lay its hand on the error locator polynomial. Find out some property that the error locator polynomial satisfies, namely that the error locator polynomial is of degree at most t, and if you multiply it pointwise with the received word, it gives rise to a polynomial of degree at most t plus k minus 1. So let's actually go ahead and step 1, find out an E and N pair that satisfy this. And then once you find this, it says just output the ratio N by E. It is amazingly simple how it's quite amazing how simple the whole thing is. Questions on the and it captures exactly with one place in the proof where the half the minimum distance comes and magically comes with and it's exactly half the minimum distance. This is exactly where it comes. So P is less than, so this algorithm will work all the way up to as long as the number of errors is strictly smaller than half the minimum distance. So I want to stare at this a little longer. I want to say actually claim to prove something stronger. Claim to proves that. So you have shown that n hat e hat is a solution. I want to say that actually what it proves is something stronger. It proves that any e that it outputs is actually a multiple of e hat. Why does it prove that?
That is the smallest degree.
Why do you know that?
Because those are the locations where the error actually happened. If you take any polynomial with smaller degree, then p times e won't be equal to e and the errors. Not mass errors.
So in particular, what we have claim 2, I want to say implies that in E step 1 is a multiple of. And what you guys say is exactly correct, because in and make this observation. Why is this true? This is just true for the following reason. So we know that E satisfies n of alpha I equals beta I equals P alpha I. But we also, what else do we know? I want to say that of course we also know that n hat of alpha I, that we know that P of alpha I into E hat of alpha I is also equal to beta I into E hat of alpha I. So that's the point which we had. So what do I want to say from this?
If p of alpha is not equals to di, then e hat of alpha is
Yeah, so this is what you guys just now said. P of alpha I is not equal to beta I. That implies P of alpha I has to be. And this is obvious from this.
so e hat
That
is usually claimed to
If you can claim to get this. Okay, because we claim to says that n by e should be equal to identically as should be equal to polynomial p. Ishan is not convincing for you.
yeah.
Therefore, you have this. Therefore, every root, and this implies that E hat alpha, E hat alpha is 0, implies E alpha is 0. So that implies that. Hence, Any solution to obtain one is actually a multiple. The only solutions we will obtain are multiples of the hat. That's what we need. Okay. Questions so far? Seems like a very simple algorithm, but we will actually use this again and again and again to get the further extension to this decoding and stuff later.
Yeah, it's not for this decoding.
Huh?
It is not for this decoding.
No, no, right now it does not. Right now it just breaks down exactly as the unique decoding. Breaks down at this point. The degree mantra tells you up to this point you can get it, and after that, I have no guarantee on it.
Like email must be in the list.
I would like to do it. I would like to do it. I don't know how to do it. We'll see. We'll actually see. Just this version of, we'll have to modify the algorithm a little more to actually get it to the list before. We'll delay that for a few more lectures. But right now, I want to ask the Berlekamp-Welch algorithm was one way to solve B. We will see yet another way to solve B, and then show that also will give you the same answer. So that's. So, and the basic part of it is very one high level. Once I say it, what the only difference between what I said so far and what I did now is whether you're working using the generator matrix point of view or the parity check point of view. What do we want? We want this E times beta. So point-wise, you are taking multiplication. The function E and the function beta. These are two functions on the evaluation set of points. You're taking a point-wise multiplication. This is usually called the Hadamard product. You want the point-wise multiplication to be a polynomial of degree at most t plus k minus 1. That's what you're trying to solve. Now, if you have some vector, you want it to be a solution to t plus k minus 1. Either you can say, either you write whatever we said, write down this evaluation thing, or if it has to be the evaluation of a t plus k minus 1 vector, it has to be orthogonal to every point in the dual of the t plus k minus 1. This one, just write those constraints. Write those constraints that the Hadamard product of beta and EI, beta and E, should be orthogonal to every dual of degree t plus k minus 1 polynomials. That will ensure that this is a degree t plus k minus. So the alternate approach is to do the following. That's just a way of solving, but all I want to say is these. The way I stated, I'm simplifying it. These are exactly the differences between the two. That's what Peterson and Berlekamp and Massey were solving, and this is what Berlekamp-Welch solves. And we will see some more extra one. And the reason I'm doing it is because this alternate way is the only way I know how to get a linear time algorithm. Right now, it's a polynomial time algorithm. To get the linear time algorithm, I will need. The only way I know currently to do it is to go via this alternate view approach of doing it, not the Berlekamp-Welch. It would be good if we can get Berlekamp-Welch to run a linear time. I don't know how to do it. As stated, I don't know how to do it. Let's go to this one. What do I want to say? So we're going to define this function E times E beta. This is what the function E times beta. This is the point-wise product. That is also called the Hadamard product. I want to say this is a member of. It is an RS feed yes what? This one, what was the degree parameter? T plus k minus 1 was the degree, T plus k. Remember, belongs. This is what we need to show. That is equivalently. E for beta is orthogonal to E solvent F S T plus T, the dual of this. Okay, that's what. So let's write down the constraint. What does this mean? To make like what I say will hold good for ES. To make life simple, I will, because dual we only saw it for certain S's. I will write it only for a particular choice of S, but everything that I say will work for any S. You guys haven't yet seen the dual for arbitrary S. That's going to be in the problem. So let's for simplicity. Yes, B F star. N is equal to minus. In this case, we know R F F star K dual. What is a dual? It's a span of the evaluation of all. Yes, for x to the power I 1 less than or equal to I less than or equal to n minus. So the evaluation, it's not resolved forward. It was you dropped out the constant vector. That's what we saw last time. So basically, we want to say E dot B is sufficient to say it's orthogonal to this, sufficient to say it's orthogonal to this set. So the conditions are can be written as for all 1 less than or equal to L less than or equal to n minus k. The k itself is n minus t minus k. Right? We should have summation going from 0 to n minus 1 e alpha I theta I. This one should be orthogonal to this is the E dot beta function, the Hadamard product, element wise product. That is the function x power I. So it should have written this. So let me write that here. Okay. So that's the function x power n, also evaluated at this. So this is what So we basically want to find E that satisfies this set of constraints. Let's write it a little more. That is, so let's E is any vector. What is E of x? E of x itself looks like a polynomial of the form e power I, x power I going from 0 to t. So let's plug that in over there. So that is summation I going from 0 to n minus 1, summation j going from 0 to t, j alpha ij beta I alpha I del equals 0. For all 1 less than or equal to L less than n minus 2 minus 3. We need this something. Let's do some change of information. Bring in J of T E J I equals 0 to minus 1 dot I alpha over J plus L I. Just rewritten the above condition. This is the linear system we need to solve. By the way, at this point of time, you can solve the linear system. There's a bunch of linear equations in the EJs. To solve it, get an E, and we have already seen Berlekamp Welch tells you that any E that you get for the system is a multiple of E hat, so you can go ahead and finish the solution. But let's actually stare at this. I want to get a little more. I want to look at this a little more closely. So, if people are you guys are with me up to this point. So I've just rewritten the linear system. Previously, I had a linear system using E and N. Now it's only a linear system in A. Of course, whenever there's a solution to this, there will be an accompanying N. That I want to say that these guys, what you have over here, are things which we actually know. What is this? This is the dot product of. Let's look at this particular quantity. What is this? This is exactly the inner product between the vector beta and the alpha j plus and the evaluation of x power j plus L on the set case. It's this inner product, isn't it? This is exactly this way. But this is this quantity. And recall what is beta. Beta is supposedly, so let's recall what is beta. Beta is purportedly evaluation of a degree K polynomial. There are some errors in it, but beta is that. What is S x L plus J? More precisely, what is L plus J? L plus J is some number. What's the lower bound of L plus J? No, lower bound. L can be as low as 1, J can be as low as 0. Therefore, L plus J is certainly at least 1. And what's its highest value it can be? N minus K. So notice, this is exactly the duals for this space of polynomials. These are exactly the basis for the duals. So in particular, if I had chosen the right, the parity check matrix, this is exactly what each of these quantities is what exactly I would have got when the parity check matrix is multiplied by the reciprocal. So let's define this quantity. Yes, okay. Let me this definition. And all I want to observe that just writing here beta 0, beta 1, all the way up to beta n minus 1. Over here, this you got, and over here I'm putting the evaluations of the degree 1 polynomial with 1 alpha square all the way up to alpha power q minus 2. This is the degree 2 polynomial. So, 1. These are monomials. So in general, this is the monomial x power n. This is the alpha power I. What you have here is alpha power I. It's that. And so that And this, what we are just observing, is this quantity is S0, S1. Yes. How many of these I have? But S1, S2, Sn minus 2. That's exactly the syndrome I get. So this thing is called, typically, if you have a parity check matrix and you have a word, when you multiply them, you get something. If it's a code word, this will be 0. Otherwise, you get some non-zero quantity here. This quantity is called the syndrome. The syndrome is wedded to a particular choice of a parity check matrix. But once you work with a nice parity check matrix, this particular, so this S which you get there is exactly the syndrome. So the equation, I want to write. Rewriting star what we have is the summation EJ, yes sir, F plus J. So this is what the E's have decided. So the Peterson algorithm, what they do is they first take the given vector beta multiplied by the parity check matrix. You get the vector, you get the syndrome S1 to yes sir, and then they say let's solve this set of equations. And of course, we know that if you solve this equation, you will get some E, and that E will be this one. Notice now you can do sort of certain clever thing. You can first find out if there is a degree 1 solution for this. You can just solve that. If you get it, you get an answer. Then you can solve a degree. If not, try a degree 2. You can keep increasing the degrees. This has a nicer way of doing it. And also, if you look at the solution, the thing which they actually exploit is the structure of this equation. This equation basically look at, you have this vector S, which is an n long vector, or n minus k long S. And this says you take this window of P, you multiply S with E, the first P guys with E, that linear combination should be 0. And if you just slide it by 1, take the same linear combination, it should be 0. Slide it by 1, take the same linear combination, it will be 0. This is what it says, because you always get this equation. Okay, well, the only choice is the choice of n over here. If you get 1 less than equal to n less than. What is the computing the syndrome itself is more than computing the syndrome itself is more than yeah, so we have to do all of this cleverly. So Berlekamp-Massey is exactly what I said just now. That's why it's quadratic. Now to get this one, they will solve. They realize both this is fast, that is this one, and they will do both of them together in n log n. But if you don't need to write down the syndrome to solve the equation, they will solve this equation without actually obtaining the writing down the syndrome. What else going on? So the latter approach, all the previous approach basically solve the system of equations. And there are various ways how to solve it. Right now, the lecture we will stop at this. We'll say there is a solution. There's a polynomial time. And Berlekamp and Massey actually what they do is they give a quadratic time algorithm which will further improve to nearly linear time. So what I will try to do in the problem set is either try to give Berlekamp-Massey or even the nearly linear time solution. If I can, I will try to break it up into parts and put it in the problem. So the first, the Peterson and all algorithm are basically they say solve the solution, solve this space. By the way, because we did Berlekamp-Welch, we know that any solution E is good enough. Otherwise, they had to argue. If you give me any solution E here, why is that solution E any good for this one? You have to give an argument. Just because we did Berlekamp-Welch already and did claim 2, we know that any E is good enough for us. We can go ahead and so the Peterson algorithms and all are basically this. The Peterson they solve step 1. Compute syndrome. S1, S2, Sn minus K. Step 2. Solve. That's satisfies. Step 3. Given E, find the set and use the ratio. Okay. Yeah, so that's I will. So the way even these there are various ways you have to find out how fast can you find E, because that's an you have to search through you have to find the videos of E. Then even after finding E, you have to do this decoding. Well, so if you want linear time, every single of these steps you have to go into and check if you can do all of them efficiently. I know it's clear that this at most cubic time is evident from what I have written here. If you want near linear time, I even quadratic time, but again, be careful in going over all of this. And that's what the other set of algorithms do. They do it more gently. Of course, the way I figured it works, it seems to work as if it works only for the set of evaluations being X star, but there's nowhere in this proof actually that only the niceness of the dual was used to write this, but you could have worked with any other dual one and you would have had the exact same proof.
So the linear time algorithm is not meant for arbitrary.
No, it's not for us.
But if we look at the dual.
No, we have a dual characterization. Same dual characterization. You will see it in the problem. So I'll tell you what a dual for. So, okay, I haven't seen this in any book. It's going to be only in your problem. So what's the dual for? What's the dual for when S is the whole field? The dual was we define the dual to be. The dual depends on the notion of the inner product. So
if you take polynomials which are 0 outside of S.
So that's not what it happens to be more this one. So right now the definition of the dual between two functions F and G, we define, so there's an underlying evaluation set. The evaluation set is F or F star. We define the dual to be this thing. F of alpha, G of alpha, alpha index. This was the notion of dual. So we change this notion of dual for arbitrary S. What we show is there exists a vector V from S to F, S to actually F star. For every element in S we are associated with a non-zero, right? So the dual is almost this. It's F of alpha, G of alpha, and E of alpha. So there is, give me an evaluation set, there exists a V, such that if I define this dual, okay, under this dual, Reed-Solomon of K is the orthogonal for Reed-Solomon n minus. We'll show that for every set, yes, there exists a V, such that if I work with this dual definition, then there's a particular choice of V, such that it makes Reed-Solomon of degree K orthogonal to Reed-Solomon of degree n minus. And then the exact thing. The only property of the dual we use is it's basically a bilinear map and it is full rank. Full rank stating that this has dimension T, that has to have dimension immensity. And this is the bilinear map certainly, and it's also full rank because full rank comes from these being non-zero. That's the only, in fact, it could have been any other more complicated bilinear function. As long as it was full rank, that's the only property of the dual, of the inner product that we, not inner product, of the bilinear form that we use to find the one. The natural inner product is just the usual dot product, but you can work with it. And you can show this. This is what the problem set will show. Problem set will show, give me a set, yes, show that there exists a V, such that I can define this, such that under this notion of a dual definition, they will nicely match. So, the PM the Peterson, BM, and subsequent improvements. Implementation. And notice why was VCH? Peterson did this for VCH. The moment he found out the error, the set of errors, notice get the code word is simple because it's binary. You just go there and just flip the value. You don't have to do far. So this subsequent error decoding kept disappears off, and once you know which are the error locations, you just have to go to the error location, flip them out. So this is why it was done in the VCH. Certain steps become easier in the VCH world. Though the previous algorithm like Peterson and all use plastic properties of VCH, but in a high level, this is what all these algorithms do. That will complete our thing on unique decoding the resolvement code. It's an amazing code. It has this one of the code which goes all the way up to unique distance. Fantastic algorithm. What we will see next lecture is not with this decoding of the how to put this story. We have talked about codes over the large alphabet. We want to now use this to construct codes over the small alphabet. Is there a process by which we can harness the power of resolvement to get to a code with smaller alphabet? So we will define a process called code concatenation. That's what we will do in the next two lectures. Yeah, let's start.